Now let's look at normal stresses when we have bending. Okay, so let's say we have beam, and this beam is subject to bending moment. Positive bending moment. So in this case, what's going to happen is, if you look at a point on the upper surface, due to this bending moment, I will have stress, compression, stress. At the bottom surface, I will also have stresses, but on the other direction, tension. So this bending moment will lead to compression at the top, tension at the bottom, and the transition between tension to compression and this cross section, stress will go to a point where sigma is 0 or there is no stress, and at that point is at the neutral axis. So maximum stress and compression is at the top, maximum compression and tension is at the bottom. So let's add letter T to say this is tension, and letter C for compression. So at this cross section, we have maximum compression and maximum tension on the outer surfaces. We are interested, as I said earlier, we are interested in calculating maximum stress. So we always calculate stress on the upper surface or the bottom surface to get maximum sigma, because the purpose of calculating stresses is to find maximum stress in the machine element so that we can choose a material with a strength that is larger than this stress. Okay, so the formula to calculate this normal stress due to bending is given by, let me go back, is given by this this formula, sigma mc over I. This c is the distance from the neutral axis. How far is the point from the neutral axis? M is the bending moment, of course, and I is the second moment of area, and it depends, of course, on the cross section area, the shape of the cross section. Is it square? Is it circular? Is it a tube? And so on. So this is sigma from bending moment. Now the other type of stress, shear stress, can be as a result of torsion, can be a result of torsion. Okay, so maximum shear stress, if you see here in the formula, we have R, and of course we have modules of rigidity, we have angle of twist, and so on. So this formula can be reduced into the equation to calculate shear stress, this equation. So in this equation, you see we say tau maximum, because we are interested in maximum shear. And the formula, you see torsion T, and R, this R is the radius, and J is the polar second moment of area, and it depends on the cross section, whether it is a circular, tube, square, and so on. So in the formula we use R, radius. That is because maximum stress happens at the top surface. You see, this is the center, and this is the top surface. So point at the top surface would have traveled from here to here because it was subject to maximum torsion, where at the center point will not move. So shear stress at the center is 0 if this is the cross section and this is the center. Shear stress at the outer surface will have maximum value, and shear stress at the center is 0. So in the formula we use R, radius, for the outside surface. Okay, so power, of course, will give us movement. So power is a result of torsion and angular velocity, and torsion or torque will lead to shear stress.